Okay, so ladies and gentlemen, I think we can get started. My name is Armagan Al-Haq. I am the Manager of Program Development, Partnerships and Finance here at University of Waterloo. And it's a privilege and honor for us to have Professor Majid Amitpur as a guest speaker for WISE. Let me introduce Professor Majid Amitpur. He is a Professor of Mechanical and Energy Engineering at KN2C University of Technology. He and his research team are working on different aspects of the energy and water integration systems through using cogeneration approaches, including systems that are utilizing renewable energies. The team is also investigating the energy systems integration with environmental issues, specifically carbon emission trading, agriculture productions that involves water, energy, and food nexus, and energy materials focusing on clean technologies. Professor Amitpur has published more than 370 national and international conference and journal articles. His book, Cogeneration and Polygeneration Systems, which was published by Elsevier Science and Technology, adopts exergetic and thermoeconomic analysis and related modeling and simulation tools to inform performance and systems design in modern cogeneration plants. He is also affiliated with University of British Columbia in Canada and Polytechnique di Milano University in Italy as a visiting professor. Ladies and gentlemen, please welcome Professor Majid Amitpur. Professor Amitpur, the stage is all yours. Please.
Okay, thank you very much. First of all, I would like to thank you, Mr. Armagan and Mrs. Sana, to invite me, and also WISE Waterloo Institute for Sustainability Energy. I would like to thank these people. Hello and good afternoon to everybody. I hope all of you are safe and in good spirits in these days. As Armagan introduced me, my name is Majid Amitpur. I am a professor of energy engineering at KNTC University of Technology. Actually, I'm working for more than 20 years at this university. My major research interests are about the process integration and polygeneration system. Actually, we applied these subjects in oil and gas industry. In recent years, we considered new research topics in water and energy and food nexuses. Today, I would like to talk about the new vision to polygeneration system in total site context, assisted with solar energy. Actually, here I give you some brief introduction to my talk today. I will talk today. First, I go to my introduction, and I briefly explain about the process integration. Then I go to explain some about the total site, polygeneration, and solar assisted system. Finally, I will give you some conclusion about my talk. Okay. Actually, key issue of this work I'm going to present today is how a combination of aspects of process integration at total site and polygeneration can work. The question is, can these tools and analysis collaborate? Yes, the answer to this question is yes, they can work pretty well. And the second question is how fossil fuel and renewable energy can be adopted. The question is it possible reconciliation and trade-off between the traditional fuels and renewable energies? The answer again is yes. There is a well-known literature about this subject, and I will show you this successful approaches which these days many people using. If we put all these aspects together, we can actually achieve to optimal global results in our work. Let's explain some about the process integration. Process integration has been commonly used as an effective tools for resource conservation and waste reduction. Professor El Halwaji, who is working in Texas A&M University, defined process integration as a holistic approach to process design, retrofitting, and operation with emphasis the unity of the process. Heat integration as a part of process integration is systematic methodology that provide a global understanding of heat utilization within the process and imply this understanding in identifying the utility targets and optimizing heat recovery as well as energy utility system. Okay, now after this explanation and definition about the process integration, I would like to explain where the process integration and cogeneration will stand in overall energy efficiency strategy. If you look at this 4 level of the energy efficiency strategy, you can see process integration and heat recovery action stand in 2nd level, and cogeneration and polygeneration, which I will discuss later, stand in 4th level. And from top to bottom, the payback period will increase, actually. So the question is how the process integration can help us. In 2 ways, we can take advantage of this procedure, this analysis, or these tools. Where are the losses? Process integration will help us to show where are the losses in your process or energy system. And the second question is, how can we make saving? And again, this analysis can help you to show how we can make saving. If you look at this slide, actually real energy demand of any process is part of the energy you supply by utility system. If you look at this picture, you see we put a lot of energy to this, we supply a lot of energy through the utility to this system. But just part of, a small part of energy we supply by utility reach to your core process. You can see the area of the below the or surrounded by the bolded curve. We have a process losses, we have a heat exchanger network losses, and you can see just part of the utility you which you spend a lot of money just reach to your process core, and we have a lot of exergy and energy losses in heat exchanger and your process losses. So about the second question, is there any how we can actually saving energy through the systematic method? Process integration give you a systematic method. You can save your energy. If you look at this slide, you can see we stand in existing design point, the green point. And if you spend some money, if you actually invest some money, you can go through the real retrofit trend curve and reduce the energy consumption. Of course, you have to invest some money, but anyway, you can reduce your energy. So process integration can give you the systematic method which you can reduce the energy by actually putting some money or spending some money to your system. So this curve shows you how you can reduce the energy by spending some money. There is a certain procedure in process integration to do such a retrofit. So the second issue I have to explain about that is total site concept. We are going to use for solving a problem. Total site energy management is a focus on solving the site-wide issue of the process and is designed to deal with the problem of how best to supply the heat and power needs of an entire plant site. This approach helps engineers in optimizing the cost and in reducing emission via better usage of invested infrastructure. So that's a concept, total site. So actually, it is new look to your system. If you look at to this total site, maybe you find it sophisticated, you find it very difficult or complicated, but I take it as an opportunity. You see, there is a lot of energy level, energy paths, different type of fuels, utility hardware, process, national grid. I take these parameters, these various parameters as an opportunity. I can manipulate energy level. I can manipulate using the fuel, a different type of fuel, or I can just work with the different type of hardware utility in my system. You can see there is a different type of process, energy level, different type of turbines. We can connect with national grid. I can see all of these as an opportunity, not as a complication. So here in left-hand side, you can see site utility system, and in right-hand side, your site processes, which demanding the utility. Interaction between utility system and process, there is a steam going on and out, and possibly you can produce or consume power. Anyway, you have to spend a lot of money in your utility system, and you should respond to the demand in your processes. Actually, no process design without considering the utility demand. These days, there is no design process without considering the utility demand. Now, here you can see sink and source profiles. In this picture, if you look at in left-hand side, you can see source profile, which is coming from your source of energy in your total site, and right-hand side, you can see sink profile, the part of your processes which need the energy. So here in right-hand side, you have to consume some steam or heat. And in left-hand side, you can generate steam. So here you can see if I want to satisfy this sink and source, actually I place the utility as a high pressure steam, medium pressure steam, and low pressure steam here. If these two curves get close to each other and we find out the interaction between their parts, you can see actually we can targeting heat and power here. Heat flow cascade and power generation. You see, the power generation is the shaded area. If you consume the fuel here, you can produce very high pressure VHP, very high pressure steam, and then you can put it through the steam turbine, and in this shaded area you can generate power, and the back pressure of this turbine can go to the process. So the shaded area show you the target of the power generation, and there is a heat flow between process and utility, and there is a steam flow in the utility system. So you can see how we related the utility system and processes. And middle of this interaction, you can generate the power, and you can target heat and power through these tools. So in next step, I'm going to explain about the cogeneration and polygeneration. Cogeneration and polygeneration are the efficient method of saving energy in which electricity, heating, cooling, and water are produced simultaneously. The heat generated from cogeneration can be used for district heating or in process industry. The simultaneous production process can be based on the use of the gas turbine, steam turbines, or combustion engines. And the primary energy source include a wide range of fossil fuels, biomass, geothermal energy, or solar energy, which solar energy we will consider today about solar energy, how we can use the solar energy in our polygeneration system. Oh, it's a general definition about the cogeneration and polygeneration system. What's new? Today we will put some new idea in cogeneration system, a new aspect in cogeneration system. Again, more opportunity we can find here is which energy path in system you are going to use. There is a lot of paths you can use in your energy system. Good news is there are thousands of ways you can use pass your energy. If you have a network of steam, there is 1,000 ways you can send your steam to your network. So it is good news for me. Let's examine those. Why you just choose the 2-3 ways? I like to examine all 1,000 ways. I will consider them, and I'm not leaving them, and I'm not going to miss the opportunity. The second question: which hardware can be used? Again, good news is there is a many type of the hardware that sequences. Again, let's choose the best configuration, and actually the best energy path and the best configuration can result in optimum result actually, and the global optimum design can actually achieve through the finding the best energy path and the best hardware sequences. Here you can see what I am talking about. Which energy path you like to choose, it is up to you. Don't worry, there is a systematic approach. We actually developed the systematic approach. You see, the turbine one, there is a two type of the actually energy you can pass to turbine one, or if you look at turbine two, there is a actually there is a four-way you can send the steam inside the turbine two. So that's a way you can actually choose which one is the best, and there is a systematic approaches to select one of them. You can assign an equation to any hardware like turbine as one of the hardware in utility system. Here is the correlation for actually turbine, and there is a slope and intersection for the turbine, and there is a correlation for each turbine. Each hardware can have a correlation. If you have a turbine network, it means you have a bundle or bunch of equation in your system. Here, I'm going to actually introduce the new tool, which we name it R-curve method. R-curve method actually generate through the energy efficiency and R ratio. If you plot a curve, you have a one axis energy cogeneration efficiency and another one R ratio. You can plot the curve, which can show you how is going in your system. Cogeneration efficiency is shaft work plus Q usage over the Q supply, and R ratio is power production over the Q usage. Now let's plot cogeneration efficiency against the R ratio. Here you can see this curve, which back to 80s can actually produce this curve. Later we actually improve this curve to manage and understand our energy system. You can see by this curve you can develop different type of the configuration, and you can actually has a good evaluation in terms of cogeneration efficiency and R ratio. R ratio show you increasing. If R ratio increase, it means you are increasing power demand, and cogeneration efficiency is obvious. If you like, of course, increase your cogeneration efficiency. You can see here each configuration give you different trend for your system. For example, you have a boiler, back pressure turbine, and condensing turbine, which has a lower cogeneration efficiency. If you can see the below curve, and the above curve has a better cogeneration efficiency, because above curve, the top curve has a gas turbine plus fully fired boiler plus back pressure turbine. So what are expecting from R-curve? Extend and improve R-curve. As I said, we improve this curve, which is back to 80s. Find out how to improve the operation of existing system. Determine the options for power import or export. You will through this methodology or curve, you can find out the best opportunity for import or export your power, indicate good direction for energy retrofit, identify promising option for debottlenecking. So here you can see example. We have solved actually, and you can see there is a lot of option. Many options can be developed for a given example, different route for each utility setup. For example, if you look at option S, we installed the turbine with 8 megawatt and boiler of 60 megawatt. Or if you look at the option, for example, B, we installed a small condensing turbine of 4.22 megawatts to improve your system. Each curve in this system show you a trend you can choose. So cogeneration efficiency against R will show you which one of these curves are the best for your system. Now let's go to solar assisted system. Like conventional CHP, solar cogeneration is ideal for facility that use a significant amount of hot water on a daily basis. Traditional CHP system heat water with the waste heat created from natural gas turbine during the electricity production. Solar cogeneration works in a similar fashion with but without using non-renewable sources. Solar cogeneration advantages over the traditional cogeneration are reduced greenhouse gas emission and a stable energy price. So I'm sure all of you believe the solar energy will reduce the greenhouse gas emission. So again, we back to total site picture, but with new vision on total site. We have a new source. We have a solar, wind. We have a different type of solar heat, PV. Also, beside the fossil fuel, we have a biofuel, and in different paper, we use different type of energy resources, and we introduce renewable energy total site and polygeneration system, and we take advantage of different. You can see different processes, different level of energy. We have a national grid over there to interact with national grid, and all of these are opportunity for us and actually to improve our system. Solar assisted system, well-known method available in the literature. Actually here we adopt one of them to our work, and actually we adopt fossil fuel and solar energy here. Here it is the procedure. I'm not going through this line procedure, but just I give you the idea where and how we can supply this procedure, show you where and how we can supply solar energy in our system. So here is one of the algorithm we use. So if you apply our all aspects introduced, I briefly introduced here, and using simulation and integration software, finally you can get your optimal design. If you are working, you as an engineer working with the simulation software and integration software, and using those concepts, finally you can find the best solution. So great collaboration between component, cogeneration, processing with solar energy, and total stack. So let's finally, I give you a case study how it's work. Here you can see the utility system in left-hand side, and we have a 4 process which this utility system actually responds to their demand. So we have a 4 process, 12 utility hardware. We have a 2 boiler, one gas turbine, 1 HRSG, and 6 steam turbine, and 2 direct drive. And we have 8 steam levels in different pressure level. And the site utility cost here is 34.38 million pound per year. It is existing operation. Actually, we went there and we investigate what's going on, and we simulated this utility system. And then using all those concepts I explained to you about the process integration, total site, and polygeneration and solar system, we actually get optimal operation for this system. If you look at this site utility cost here is 34.38 million pounds per year, and then we reduce this to 29.48 million pounds per year, which if you convert it to Canadian dollar, it is about $10 million saving. Using this approach easily, mostly it is just software things, we achieve to $10 million say Canadian dollar saving in this actually utility system. Take advantage of those procedure I explained to you easily through that method. So I go to conclusion. Here, process integration and total site concept have been improved polygeneration system outputs. Methodology has taken advantage of renewable energy to make new design more efficient. Each of above aspect had their own benefits, and we used that. Introducing renewable energy to traditional system to make cleaner technologies. Actually, by introduce the solar energy, we adopt the solar energy to cleaner to fossil fuel system. Better understanding of process. Actually, we are claiming this approach are conceptual, and we are claim we have a better understanding compared to pure mathematical method. There is a lot of people working this area through the mathematical modeling and superstructure. More reliable and flexible system in terms of control and safety. Yes. For example, less demand from national grid. One of the achievement here is less demand from national grid. That's why we reduce the cost of utility. And simplified operation. Actually, if we go to this utility system, we eliminate 2 turbines from that system. So we actually simplified operation for this system. Finally, approach can save millions of dollars. So we could save millions of dollars. Actually, in this case study we solved, we saved $10 million. So here you can see some references we used. One of very important references here is Chemical Process Design and Integration, written by Professor Robin Smith, it's published by Wiley, and we also publish many papers and the otherwise. publish a lot of paper in this area. So thank you for your attention. If there is any question and comment, I am ready to to answer.
Professor Amitpur, thank you so much for your wonderful presentation and sharing some great insights with us. Actually, I have a quick question.
Yes.
You talked about total sites and polygeneration concepts.
Yeah.
Actually, at one point, University of Waterloo, here at University of Waterloo, Professor Natwani was considering a refugee camp in Kenya or in Uganda. And he wanted to see if there's a possibility to use mathematical modeling or any optimization technique to support the refugee camps with the help of solar PV panels. And in combination with biofuel or geothermal electricity at a very smaller scale. I just wanted to get your feedback if that's a good project and total site concepts and polygeneration concept can help to optimize a project like this.
Okay, actually, yes, it is. When you have a, when we are talking about the total site and polygeneration, we are talking different type of source of energy, and we are expert about how we can optimize this different type of resources, and how we can reduce the CO2 emission, how we can reduce the cost for this such a operation. In my experience, we usually we take this polygeneration or total system beside the big factory, big processes. But you are talking about the camp or small places. So why we don't consider making this camp close to some municipal facility or industrial facility? Possibly we can have a some sort of cogeneration. I'm talking about the location is very important.
Mm-hmm.
You know, where we are, which country we are. Is it solar is important there, wind is important there. We have a source of geothermal. Is there any hospital is close? Is there any factory is close? The location and the layout of your system is very important for total site system. We are close to national grid. How is the national grid? National grid electricity cost is high. There is a lot of parameters. If you look at this slide, and it is the total site new vision. It is very complicated and sophisticated problem. There is a 6 processes, there is a different level of the energy, there is a different type of energy. Of course, many of these elements, components will eliminate it when you go to, for example, Africa. Many these elements will disappear, and actually in terms of mathematics, your problem will be simplified actually. So it is depend on where we shall go and what resource. We have a great approach here. We have a great approach, develop a very good approach here, and you have to give us the what's your resources, what's your equipment, hardware's equipments, and what the resources we can solve it and give you the idea of which combination of the resources and which network of the hardware are the best for you.
Perfect. Perfect, Professor Amitpur. And there is one more question. One of our postdocs from the Department of Electrical and Computer Engineering, he just texted me and he said, Professor Amitpur, thank you so much for your presentation. And he's saying that, Professor Amitpur, you have talked about national grid cost optimization. Is it possible to use the techniques you have mentioned for basically optimizing grid stability and power quality control?
Um, Actually, possibly we haven't done that. There is a possibility. You see, we are talking about the solar energy and wind power inside our system.
Mm-hmm.
And we are talking about the national grid as an external factor.
Okay.
So if we consider, exactly, if you look at the boundary of this slide, I don't know you have my slide or no. If you look at this slide, you see grid is outside our system.
Mm-hmm.
So if include the national grid in our system, yes, we don't have such an experience. It is new for me, these questions. If we actually extend our boundary of the operation to national grid, or put some parameter from a national grid to our system, yes, we can. But I don't have experience. It is very good question. Actually, maybe we can work on it. It is very interesting, actually. But, at the moment, we look at the national grid as an external parameters.
Mm-hmm.
Why not? It's an excellent question, actually. Why not we consider national grid as a part of our system?
Mm-hmm.
Yeah. Let's see what happens. Maybe, of course, we are mechanical engineer, and we need some electrical engineer to involve for such a great work.
Yeah, I guess Professor Ahmedpour, that could be another thesis project, I guess.
Oh yeah, yes. Actually, it is a. I feel it is a PhD thesis. Actually.
Yes, I agree.
Yeah. Yes, it is a great job. Yeah.
Perfect. No, thank you so much, Professor Ahmedpour. A couple of texts I am receiving. I think some of our grad students are having difficulty in getting in.
Oh, okay.
So I will actually send an email to everybody that Professor Ahmedpour's PowerPoint presentation will be posted soon in about 15-20 minutes to our WISE website. And if they have any questions, they can always get in touch with you.
Oh yeah. Also, I believe you record this, and possibly later they can have a look to this presentation later.
Yes, Professor Ahmedpour, and particularly slide number 24, which you are actually showing right now, the entire schematic process. So I would like to inform all our grad students and postdocs that Professor Ahmedpour would be very much reachable to you guys, and the presentation will be posted probably by 3:40, 3:45 today. So you would be able to have a quick look, and you would be able to get in touch with Professor Ahmedpour.
Okay, of course. I will email my presentation to you, and you can share it with your student or your research fellow.
Perfect. Professor Ahmedpour, thank you so very much, sir, for your time and for your presentation. And hopefully we would be able to collaborate in the future, and a lot of projects will happen soon.
Yes, I love to collaborate with WISE, and thank you very much, Armagan, and thank you, Sana.
Thank you, sir. Thank you so much.
Thank you very much. Thank you very much. Bye-bye. Bye.
Have a great day, sir. Bye-bye.
Great. Right.